minus 34 times 3e8 divided by, now I need a parenthesis there, right? And that's 1e6 times 1.602 e minus 19, right? That's 2 half-million electron volt electrons, right? So to make an electron, it's 2 times 0.511 MeV is about 1 MeV, yeah? Isn't that right? So this is the energy needed to create an electron and a positron. This is the cheapest lepton to make. All the other ones are more expensive. This is the cheapest one. So when you're out of this business, you're out of the lepton business. And all the other leptons, by the way, decay into electrons eventually. Do you guys get the temperature is about 2 times 10 to the 9th? Yeah? Where do you suppose that is? Do you suppose that's like right about there? Yeah, 10 to the 10th is here. This thing's like 10 to the 9th or so. Did anybody else get that? Yeah? Did anybody do it the long way to make sure that like this wasn't wrong?
I did it that way, yeah.
You did this way? All right, that's good. It's good that we're getting the same thing, right? Okay. And then for the final thing, just hit second entry, go in and change this instead of 1 times 10 to the 6th. Change this to 1.3, I mean just literally 1.3, right? So the same exact thing, and now we're 1.3 electron volts. If you've got less energy than 1.3 electron volts, then basically you don't have enough energy to even ionize matter, right? So we're going from plasma to not plasma. So we're finding the temperature of this guy right here, okay? So go ahead and do that. I'm going to go second entry, and I'm going to go back and change 1e6 to 1.3. And I just got about 3,000 kelvins. Right? I typed this in, only it's now, this is 1.3 literally, right? Electron volts. So you guys get about 3,000 kelvins. 1.3 is the energy basically needed to ionize matter. If you've got more than 1.3, you're going to ionize, every collision is going to ionize, right? Below that, above that it's plasma, below that it's not, right? Okay. Do you guys get about 3,000 kelvins? So that's why cosmologists talk about, equally they'll talk about time, but oftentimes they'll talk about temperature. A particular temperature corresponds to a certain fundamental particle that can be created or destroyed. What are you getting?
7 times 10 to the 40th.
Oh God. You know?
Oh wait, I forgot it's divided.
That's too hot. But that temperature is on the chart there. That's the interesting temperature. Yeah. No, it's an asymptote. Okay, now I'm going to hit the right arrow. There's some interesting things to talk about, but the real interesting stuff is masses. Notice that this is all we need to get off of this. Notice that these guys, of these baryons, these guys are actually unstable and decay into these guys. Even free neutrons in atoms are stable, but free neutrons will decay into protons eventually, right? And then electrons are part of a family of things, right? Muons decay into electrons, taus decay into muons and electrons, right? And so, yeah.
There's two things that is neutrino up there twice?
Yeah, there's all sorts of neutrinos. There's electron, tau, and mu neutrinos. It's crazy. 3 different varieties.
What are mesons?
Mesons. Just your book's got a really good section on particle physics. I don't have the time to go into it, but they're a part of the hadron family. All right. So if we go back far enough, so this is, cosmologists have 2 different kinds of time machines. The first is a telescope, and you look far away from the Earth and see light, ancient light. Yes? Okay. So it's a bit like paleontologists could see somehow dinosaur bones or something like that, right? When you see this light from far away, it's ancient light, and it tells us all sorts of things. The other time machine we have is particle accelerators, because as you go back in time, you're going to larger and larger energies, aren't you? Larger and larger energies allow larger particles that are unstable to be created that haven't been created for a long, long time. right? So that's what they're doing. That's what particle accelerators are doing. And before 10 to the minus 34th seconds, relativity doesn't work because it's like the space-time is too curved, and it generates infinities, right? We don't yet have a quantum theory of gravity, right? We think, though, that this was a grand unified thing, that the four forces of nature were unified: gravity, electromagnetic, weak nuclear. Say it again? And they, yes, that's true, right? Okay, at this point, suddenly, okay, in this region, gravity condenses out, okay, and what we're talking about here is the particles, okay? The particles that mediate these forces have done in some interaction where they are now free particles, right? The fundamental particles, though, are all pretty much the same, okay? Now we're getting down to some real time periods here, right? 10 to the minus 4th second, I mean, that's just like forever, right? Can you believe how long he took to explain that? He took like 10 to the minus 4th seconds. Yeah. It's like, geez. Okay. Strong nuclear force finally separates out, right? Quarks are confined, because baby, when those quarks are not confined, you know, geez. It's really hard to say anything, right? Okay. This is the hadron era. As soon as you confine quarks, hadrons and all matter, right, are made of quarks, right? And we already calculated the energy of these photons, right? And it's roughly matter and antimatter being created and destroyed. However, we know somehow more matter was somehow created. And so when everybody picked a dance partner at the end of the hadron era, right? When everybody picked a dance partner, there was more matter dance partners than antimatter. And it's like, damn, nobody to dance with, right? There's a slight imbalance of matter. We think it's about a part in a billion. What we had left is 1 part in a billion of the matter that was running around then. It's just it was antimatter and matter, right? So it's like a bar graph. Here's your bar graph, right? Here's matter, here's antimatter, right? This thing is 1 part in a billion taller than this thing, and so when it canceled off, that was what was left, yeah? 1 part in a billion. Okay? Now we're getting to some real time. 10 seconds, right? You can get bored in 10 seconds. Some people can, right? Okay. Photon energy drops below the mass of hadrons. Hadron matter annihilates hadron antimatter. What was that?
I don't know.
Okay. This is called the lepton era. Basically, you've got electrons, positrons, neutrinos, and a ton of photons running around. Okay. It's a lepton eat lepton universe, right? Positron, matter leptons eating antimatter leptons, right? And now, you know, this is, instead of 500,000 years, it's 0.38 million years, right? This is our more accurate thing, right? Thermal energy drops below the mass of leptons. The leptons condense out. So we're talking about just condensation, basically, right? Okay? Leptons being the last ones to condense out, right? And we still have a little bit of matter left. That's a good thing, right? Otherwise, none of this would matter, right?
Yeah. Oh, I didn't get that. Murray.
All right, and now we're to the present, right? Thermal energy drops below the binding energy of atomic electrons. What does that mean? That means that before now, photons were stripping off electrons from atoms willy-nilly. After that, they couldn't. And so the electrons all went, ooh, we want to be in these resonant standing waves, probabilistic waves around nuclei. They are bound to the atoms, right? Now matter becomes transparent, and it's from then that we can see the universe. We can't see this part. That's why we've got particle accelerators to make conditions like that. Okay. Somebody's moving desks or something. Atoms are born. Atoms have to have electrons on them, don't they? Neutral atoms are born, right? Nuclei were born before this, right? But atoms are born at this juncture here. So you could label that little thing there, birth of atoms. Birth of neutral atoms, if it bothers you, if you think that a nucleus is an atom, which I sort of do. Okay? Now,
What are you doing out there, man?
giving blood.
No, she's just getting snapped.
That's what that noise was a kid ripping stuff off their arm before they went into class. That's what that noise was, wasn't it? Didn't we hear like a ripping sound? Yes.
We should earthquake on Wednesday. We should earthquake out there.
Okay. Now,
Oh, then I'd have to retake it.
class. I know it's exciting when Megan walks in the room, but we have to.
Don't just say no.
That's how bored you are, right? It's like,